Okay, so I will briefly present the H of t reconstruction. So the reconstruction of the strain value, which is equivalent to the amplitude of gravitational waves when it passes on Virgo detector. So the outline is the following. I will first describe the principle of this H of t reconstruction, and then the new functionalities that we have developed for the O4 run, and the performance we obtain for the latency and uncertainty of the H of t reconstruction. So first, why do we need to reconstruct H of t? In fact, the Virgo interferometer deliver on what we call the dark fringe port a quantity of light which depends on the difference of length between the two arms, and this is proportional to the amplitude of gravitational waves. But we have also longitudinal controls of the interferometer mirrors to keep the interferometer on the working point. And so part of this gravitational wave signals is in the control loops. And so we need to reconstruct from the dark fringe signal and from the control loop signals what is the real gravitational wave amplitude. So how we do this is with a HREC process, which is working online to reconstruct the H of t. So this is a process initially developed by Benoit Mours, and it's working in the frequency domain. So what we do is to use a model of the actuators of the mirrors and a model of the optical response of the interferometer for each mirror motion. And we pass the control loop signal for each mirror into those two transfer functions, the model of the actuator and the model of the optical response. And it gives us a contribution that is to be subtracted to the dark fringe signal, and the result is then applied to an inverse transfer function of the optical response of the interferometer to get finally the motion of the mirror due to gravitational wave, and so the H of t. And the HREC is able also to do the reprocessing online if needed. So we use a calibration actuator model, which is provided by the calibration team. So we use a reference which is called the photon calibrator, which allows us to calibrate each actuator of each mirror with a good accuracy. And once we have this model, which is made of one gain, one delay, and a set of poles and zeros, we can apply it to the H of t reconstruction. And for the optical response, we have also a set, periodically we have a set of optical response measurement by injecting some noise at the level of each mirror and looking at the dark fringe when we inject this noise, and we determine the transfer function between motion of the mirror and the dark fringe signal, which is what we call the optical response. And I showed here the one example of a fit that we do on optical response measurement. And from this fit, which is just a simple pole optical response model, we get a pole frequency, an optical gain, and then during the H of t reconstruction, we apply permanently some lines. We inject some lines on each mirror. And this allows us to adjust this optical response model, not to take this a single one, but to adjust every 4 seconds. We adjust the parameters, the pole frequency and the optical gain, which are varying when the alignment of the interferometer is varying. I will skip this. So new functionalities in HREC, there are three main new functionalities. This is online subtraction of the of the noise in the interferometer. We have a new method for O4, and also we have the possibility to apply a different optical response model for each mirror, and we apply also an online unbiasing, and I will explain what we do to do this online unbiasing. So we perform every week injections. We inject on each mirror lines, so sinusoidal signals at different frequencies. And when we do those injections, we are able, knowing the actuator model for this mirror, to reconstruct what would be the real H of t corresponding to this injection, what we call a H-inj. And we look at what is reconstructed by HREC, so what we call HREC, and the ratio between the two should be 1 for the modulus and 0 for and 0 for the phase. So you see here the bias, so the HREC over H-inj for different frequencies using the different mirrors, north end, west end, and also using the Pascal at north end and west end. And so we set a bias which is frequency dependent, and knowing this bias, we can apply this to the H of t reconstruction, and so provide finally a H of t which is unbiased. And you see here that the bias that is due to different, which has different origins, not always understood, but at least measured, and then we do the online unbiasing. And in addition to this, we do a permanent monitoring. We inject permanently lines, which allows us to follow the unbiased H of t, and to see that this unbiasing is working correctly and is providing an unbiased H of t within the uncertainties of the H of t reconstruction. And here I just show you briefly over the full O4B run what is the bias on modulus and bias on phase, and also uncertainty on the modulus and uncertainty on the phase of H of t. And you see that month after month, this bias is not varying too much, and the same for the uncertainties. We have a very stable value for the bias and uncertainty. So finally, we have a current H of t reconstruction, which is provided with a good uncertainty. You see here the purple band, which is showing this uncertainty around the dark line, which is showing the bias, the residual bias after online unbiasing. And so we have an uncertainty of about 2.5% on the modulus and below 100 milliradian for the phase. And part of this uncertainty is coming from the Pascal, the photon calibrator power calibration. But the main part is coming from the way we do the reconstruction of H of t, so from HREC. And we suspect that it is mainly due to the optical response model, which is not exactly the correct one. So the aim is for future runs is to have an uncertainty down to 1% level for the modulus and 20 milliradian level for the phase. And this will be useful for instance, for parameter estimation when we do detection with the ISNR. We need better precision for the calibration for H of t uncertainties. And the second point on which H of t needs to be also improved is the latency of H of t reconstruction. So currently, since we are doing FFTs, we are working in the frequency domain, we are doing FFTs over 8 seconds. So the latency, it introduces a latency of at least 8 seconds. So during 04, the Virgo HREC delivered the H of t with a latency of about 9 seconds. And this is about 1/3 of the total latency of the alerts delivered by Virgo and LIGO. And our aim, of course, is to reduce this latency at the level of maybe 1 second. This will be useful for, at least for the early warning alerts that are planned, that are alerts sent to the telescope before the BNS merger is reached. So instead of waiting the end of the gravitational wave signal, we send an alert as soon as we have a sufficient SNR in the signal detected. But for this, we need to be much better in the latency. So we have 2 options to improve this latency. The first option is to keep H of t reconstruction in the frequency domain, but doing short time windows for the FFT and using zero padding. And second option is to use in time domain ER filters to apply the actuators model and optical response model. And finally, but we need also a non-causal final filter, but which can be done with short FFTs. For the first option, we have developed and improved the HREC, which was compared to the H of t currently provided. So you see in orange what is provided by the new H of t, and in blue what is provided by the current H of t, and you see a difference. Below you see the transfer function between the two, and you see that between at low frequency between 10 Hz and 40 Hz, we have a discrepancy between the two, and we are still trying to understand why there is this discrepancy. And of course, we would like to maybe to keep this reconstruction in frequency domain, because it's much easier to be used for offline reprocessing. And just to add that most of the work on this has been done by Brian Huchon during his master internship. And also the second option was tested. We have, this is also Brian Huchon work. He has done a process which is connected to the Virgo framework real-time control environment, and using this process was able to obtain a latency which is 0.3 millisecond. And behind this, we need to apply a high-pass filter. I don't go into the detail, but this high-pass filter introduces latency of about 1 second. And the result is this one. You can see that both the H of t coming from this HREC SCL and coming from the old HREC are similar. And if we do the transfer function between the two, we have something which is very near to 1 for the modulus and near to 0 for the phase. If we do the difference between the two and the FFT, we see the green spectrum, which is much at the level of the 1% of the H of t spectrum. So this is the first result, which looks promising. So as a conclusion, we have a new HREC running online continuously since April of last year. It provides H of t unbiased, with a bias which is a very small residual bias, very small and very stable. And we have uncertainties with those values in the frequency band 10 to 1000 Hz, and work is ongoing to reduce this uncertainty. And for the latency, we have provided the H of t to data analysis pipelines with an H of t below 10 seconds. And we plan to would use one of the two options to try to go down to 1 second for this latency. And of course, keeping uncertainty of h of t as low as possible. That's all.